Assalamualaikum and hello everyone. My name is ADRINA binti Abdul Karim and I'm one of the exchange students from Malaysia for this subject. First of all, let me introduce to you my hardworking groupmate which is Abel atau STANLEY MOLUMBUNG and ZAQUAN bin ZAKARIA, and we are from Group 4 Malaysia. Here we are going to present about the size distribution of mineral. Starting from the background, follow up by methodology, result and discussion, and finally conclusion. So let us start from the background. So our group chose copper ore as the most abundant mineral ore in Malaysia. Copper is an element chemical number 29 on the periodic table of elements. The copper element symbol is Cu from the Latin cuprum. It is a ductile metal with a reddish brown color. It is also applied widely due to its high thermal and electrical conductivity. There are several characteristics of copper. These are the characteristics of copper: high thermal and electrical conductivity. Copper is an excellent conductor of heat and electricity. For this point, we know that copper is an excellent conductor for wiring and heat transfer application. Making widely used in electrical wiring and heat transfer application. Copper is a soft and malleable metal. It is malleability and easily hammered and molded into various shapes without breaking. It is also can be drawn into thin wires without losing its strength. Third one is corrosion characteristic. Do you know that copper has a natural ability to form a protective layer called patina? When it reacts with the environment, copper is an excellent conductor from the further corrosion. This making widely used in electrical wiring and heat transfer application. Last one is have high malleability and ductility. Copper has a relatively high melting point of 1083 meaning that it can be allowing it to withstand high temperature without melting and losing its structure. These are the characteristics of.
Next, I'm going to explain methodology. Assalamualaikum, my name is ZAQUAN bin ZAKARIA. I'm going to explain you a mineral reduction of copper ore. So basically, the solid material of copper had a density of 8.94 gram over cm cube. So the maximum fit particle size of copper for primary crunching is about 100 to 200 millimeter, and the final product will give a 0.5 until 1 millimeter in ball milling. So here is a working mechanism of copper ore. Copper reduction involves reducing the size of mineral particle to a smaller size. This is also known as comminution. There are several different mechanisms by which copper reduction can occur, but they all can be classified into three main categories, which is shear, impact and compression. For our first primary grinder, we use jaw crusher. This mechanism involves breaking up copper particles by applying a sudden force to them. High amount of force required to break a copper particle due to highly ductile particle of copper. In this situation, we use two jaws that move against each other to crush copper particles. So we are going to look into a last step of crusher, which is ball mill. A ball mill is a rotating cylindrical device used to grind material like copper ore into fine powder. Inside the mill, copper ore and grinding media such as ball or rod are placed. As the mill rotates, the grinding media crush and grind the ore into smaller particles. The rotation of the mill causes the material to be ground to the desired fineness. The crushed copper material is then further processed based on the desired end product, such as refining for metal extraction or further grinding for specific application. So the next I'm going to explain a PFD, a process flow diagram for copper reduction. The first step is mining and crushing. The process usually begins with the extraction of copper ore from mine. The ore is then crushed into smaller pieces. The next step is grinding. The crushed ore undergoes grinding in ball mill. This step reduces the ore into the smaller particle, increasing its surface area. The next step is flotation. In some cases, flotation is employed to separate the copper mineral from other material in the ore. The next step is smelting. Smelting, the concentrated copper ore, usually in the form of fine powder, undergoes smelting. This process involves heating the ore to high temperature, allowing the copper to melt and separate from impurity, forming a molten copper material. Fifth step is refining. The molten copper obtained from smelting undergoes further refining process to remove impurities such as sulfur, iron, and other elements. This can involve processes like electrolysis or other refining technique to obtain high purity copper. The last step is forming and application. Once refined, the copper can be shaped into various forms based on its intended application. It's then utilized across industry in manufacturing, electronic, construction, and more. This PEFD involves reducing copper ore from its raw form to refine copper suitable from various industry applications within the realm of particle technology.
We know that our secondary crusher is ball mill. Now we can calculate the size distribution of particle. To calculate the size distribution of the particle, we must have the cumulative passes data. So this is our data from the Journal of Copper Ore. First and foremost, we need to calculate the mass balance of the crusher in and out. So for the basis, in journal, we found out that our final product of copper ore is 6.5 ton per hour. Then we convert it into kg per hour, which is 5,900. To ease the calculation, we use 6,000 kg per hour as our basis. And our mass ratio is 1.75 kg per kg. First, we need to calculate the mass of the recycle, which is mass of ratio divided by mass flow rate of final product. And we got it 10,500 kg per hour. For mass grain feed, we must use the formula mass recycle plus with mass final product. Noted that mass grain product is equal to mass grain feed, which is the mass recycle plus with mass final product. So finally, for the mass fresh feed, we must minus the mass grain feed to mass recycle, and we got the answer 6,000 kg per hour. Before we calculate the mass of each mesh, first of all, do you remember that we have the cumulative passes in percentage data? So we need to convert it first into kg per hour. The formula that we use is cumulative passes in percentage divided by 100 and times with the final product. And that's how we got the cumulative passes in fresh feed for mesh negative 25. Repeat the whole process calculation for grinder product, oversized final product of cumulative passes in kg per hour for each mesh. After the calculation of conversion before, now we can finally calculate the mass of each mesh. So this is the sample calculation for mesh negative 25 in fresh feed. The formula that we use is cumulative passes before in kg per hour minus with the cumulative passes after in kg per hour. So from the previous data, we minus the 6,000 to 5,655.6 and we got the answer 344.4 kg. This is the mass of mesh in fresh feed. So repeat the calculation for grinder product, oversized final product, and grinder feed. Don't forget to total up in each category. So next we must calculate the mass of frequency. This is the sample calculation for mesh negative 25 for mass of frequency in fresh feed. So the calculation is mass of the fresh feed kg divided by 100 times with the total mass of fresh feed. So we got it 5.74 percentage. Then repeat the whole calculation for grinder product, oversized, final product, and grinder feed for each mesh. To know the shape of the graph, we must know that the undersized and oversized fraction. So the formula that we use in the sample calculation for mesh negative 35 in grinder feed is undersized fraction before minus with the mass frequency grinder feed at mesh negative 25, which is 100 minus 8.3646 and we got a 91.53636 percentage. Next, we must calculate the oversized frequency. But before that, we must calculate the delta diameter by using the formula whole size negative minus with whole size positive. Now we can calculate the oversized frequency for grinder feed and final product. This is the sample calculation for mesh negative 25 in grinder feed. So the formula that we use is mass frequency grinder feed divided by 100 times with delta diameter. And the data, the calculation that we got is 0.000769. After the whole calculation that have been made, now we can finally make our graph. So this is our cumulative distribution graph for undersize and oversize. Other than that, we can also do the frequency distribution graph. So this is our frequency distribution graph for grinder feed and final product. Next, we need to know the calculation for the energy estimation by using Bond's law. So in Bond's law, we need to know first the data of the index bond, dPa and dPb of 80% before we substitute into the Bond's law equation. So in our journal, we found out that our index bond of copper is 14. Next, we can calculate the dPa and dPb first. So for dPa, the calculation that we use is that we interpolate the data of cumulative passes for grinder product between the data 74.5% for whole size 4 to 5 micrometer and 87% for whole size 500 micrometer. So from the interpolation method, we found out that our dPa is 456.26 micrometer, which is the same as 0.456 millimeter. Same as cumulative passes for grinder feed, which is dPb, we interpolate the data between 60.72% for whole size 4 to 5 micrometer and 88.52% for whole size 500 micrometer. By interpolation at 80%, we found out our dPb is 477 micrometer, which is has the same as the 0.5457 millimeter. The final calculation in the size distribution, which is the average weight diameter, for the sample calculation for the mesh -25, the weight of the final product, we use the formula mass of fraction final product times with the average diameter, then divided by 100. And we got it the answer 11.0531 micrometer. Repeat the whole calculation for final product and grinder feed for each mesh. Don't forget to total up the whole average weight because that is the final answer of the average weight diameter. So for the final product of average weight, we got it 349.754 micrometer, and for grinder feed it's 418.95 micrometer.
Let's talk about the discussion. Alright, so for the cumulative passes, the smaller mesh, -30 to 60, -60 have a lower cumulative percentage of material passing through the holes, indicating effective grinding. So this suggests that the grinding process is breaking down the larger particles into smaller ones. So the second one is the cumulative passes percentage of oversize decreases as the mesh size decreases. This also shows that the grinding process is successful in reducing the the amount of oversized material, which is typically undesirable in mineral processing. Let's talk about the cumulative distribution undersize graph. Okay, the blue line slope upwards as the average hole increases. It may suggest that the coarser feed material is more difficult to grind to a finer size. The orange line also slope upwards with increasing average hole size. This also means that achieving a finer product becomes more challenging as the hole size increases. Now we move on to the cumulative distribution oversize graph. So for the final product, uses average hole size of the orange line. As the average hole size increases, the cumulative also for the final product also decreases. This indicates that achieving a final product becomes easier with larger average hole size. For the blue line, the average hole size increases, the cumulative oversize fraction for the grinder feed decreases. This suggests that a larger average hole size result in smaller proportion of material being oversized, which is positive outcome for the grinding process. Okay, now next is frequency distribution grinder feed graph. As the delta diameter increases, moving from 50 to 250, the oversize frequency for grinder feed generally decreases. This shows that larger change in delta diameter, result in lower frequency of oversized particle in the grinder feed. A smaller oversized frequency suggests that the grinding process is better at controlling the size of particles, leading to fewer particles falling into the oversized category. Okay, next is frequency distribution final product, the graph. As the delta diameter increases, moving from 50 to 250, the oversized frequency for the final product show different trends. There is no consistent pattern of decrease or increase in oversized frequency with increasing delta diameter. So this data exhibits a certain level of variability in the oversized frequency for final product across different delta diameter values. Some delta diameter values result in relatively low oversized frequencies, while other result in higher oversized frequencies. So for the energy estimation, the difference between DPA and also DPB is small, indicating that the grinding process is efficient in reducing the particle size from grinder feed to grinder product. So the cumulative passes for grinder product are higher than those for grinder feed at the same hole size, 425 and 500. This suggests that the grinding process is effectively reducing the particle size as more material is passing through the specified hole size in the product compared to the feed. For the average weight diameter, the AWD for the final product, which is 0.34975 mm, is smaller than the AWD for the grinder feed, 0.4189 mm. So this indicates that the grinding process is effective in reducing the particle size, as the average particle size of the final product is smaller than that of the feed material.
Next is conclusion. Certainly, in copper ore reduction within particle technology, the use of processes like ball milling play a crucial role. Through such technique, copper ore is effectively reduced in size, enhancing its surface area for subsequent processes. This reduction facilitates increased exposure of the ore to further extraction method or refining process, optimizing the efficiency of copper extraction and utilization in various industries.